Every atom of gold you have ever touched was forged in a catastrophe. Not a star, not a supernova. Something rarer and more violent than either. A collision between two of the densest objects the universe has ever produced. Objects so extreme that the physics inside them remains to this day genuinely unknown. Neutron stars. They begin where other things end. A massive star, one with many times the mass of our sun, spends millions of years in a state of controlled tension. Gravity pulls inward, nuclear fusion pushes back. For as long as that balance holds, the star burns steadily, fusing hydrogen into helium, helium into carbon, carbon into heavier and heavier elements in a chain that accelerates as the star ages. Carbon burns to neon in centuries, neon to oxygen in a year, oxygen to silicon in months, silicon to iron in a single day. And then the chain stops. Iron is where fusion ends. It absorbs energy rather than releasing it. Nuclear ash, incapable of burning. The moment the core becomes iron, fusion halts, and the outward pressure that has held the star together for millions of years simply disappears. What follows takes less than a second. The core collapses. The outer layers fall inward at a quarter of the speed of light. Electrons and protons, particles that fundamentally resist proximity, are forced together by pressure so extreme that they merge into neutrons. A ball of iron the size of Earth is compressed in moments into a sphere of pure nuclear matter roughly 25 kilometers across. The infalling outer layers crash into this newly formed core and rebound. A shockwave explodes outward through the star, ejecting everything above the core into space. We call this a supernova. For a brief period, it outshines the entire galaxy it inhabits. What remains is the neutron star, roughly 1.4 times the mass of our sun, 25 kilometers wide, so dense that a single cubic centimeter of its interior contains the mass of an entire mountain range. Its surface temperature reaches 1,000,000 degrees, more than 160 times hotter than the surface of our sun. Its gravity is the most powerful known to exist outside of a black hole. In fact, if a neutron star accumulated only slightly more mass, the distinction would cease to exist. The interior of a neutron star is one of the last genuinely unresolved problems in fundamental physics. The outer crust is iron, the same iron left behind by the supernova, compressed into a rigid crystal lattice with a sea of electrons flowing through it. Deeper, protons convert to neutrons under increasing pressure. At the base of the crust, nuclei are squeezed so tightly together that they deform, elongating into cylinders and sheets, enormous nuclear structures containing millions of particles. Physicists call this nuclear pasta. It may be the strongest material that can exist anywhere in the universe. Below the pasta, the core. Here our models break down. The density exceeds anything we can replicate experimentally. Protons and neutrons may dissolve into a free sea of quarks. No one knows what occupies the center of a neutron star. That is where science is actively working. When a neutron star first forms, conservation of angular momentum spins it to extraordinary speeds. Some rotate hundreds of times per second. Their powerful magnetic fields generate beams of radio waves that sweep space like lighthouses. Every time the beam crosses our line of sight, we detect a pulse. We call these objects pulsars. More than 3,000 are now cataloged in the Milky Way alone. The most magnetically intense neutron stars, magnetars, possess fields a quadrillion times stronger than Earth's own magnetic field. But the most consequential events occur when two neutron stars find each other. Bound in a decaying orbit, they spiral inward over millions of years, losing energy as gravitational waves, ripples in the fabric of space-time. Eventually, they collide. The explosion that follows, a kilonova, was directly observed for the first time in 2017. When gravitational wave detectors and optical telescopes watch two neutron stars merge 130 million light-years away. In the aftermath of that collision, astronomers detected the unmistakable signatures of gold, platinum, and uranium being synthesized in real time. Every heavy element of that kind in existence was made this way. The gold in a ring, the platinum in a circuit board, the uranium in a reactor. Each of those atoms passed through a neutron star collision before it ever reached this solar system. They traveled for billions of years, through space, through clouds, through the formation of our sun and planets, before arriving here. We are downstream of catastrophes we will never witness. And the atoms that make that possible were forged in the most violent collisions the universe allows.